Hey guys, we're looking at step up 8 today. It's using expressions to describe patterns. So you're going to see something that you've seen for a long time. They're kind of those in and out patterns. So it says you can write an expression to describe the pattern of an in and out table, which we have right here. In and out. First, look at the input and output values in the table. Ask yourself, what do I need to do to the input to get to the output? So from 11 to 6, it's going down. So if it's going down, we know we're either dividing or subtracting. So we can look at it first and kind of eyeball and think, okay, I can't divide 11 to anything to get to 6, at least not a whole number. But I could certainly subtract it. So I can subtract 5 from 11 to get to 6. Okay, so that makes sense for the first one, but we have to double check and make sense for every other one. 12 minus 5 is 7. Yep. 13 minus 5 is 8. Perfect. So we know our rule is going to be minus 5. In this table, you can subtract 5 to get from 11 to 6, so on and so forth. So then our rule is going to be, if we want to say this is x, and then this is y, x minus 5 equals y. And then we have to figure out, well, if x in this case is 15, 15 minus 5 is 10. If x in this case is 20, minus 5 is 15. So again, we're replacing the in and out. Instead of in, we say x. Instead of out, we'd say y. And we have to kind of find that rule that goes with it. So for this one, we have our in starts at 6 and goes to 18. Okay, well, we know it's going up, so it's either going to be addition or multiplication. So let's try addition first. 6 plus 1 equals 18. Well, 6 plus 10 is 16, plus another 2 is 18. So 6 plus 12 is 18. So our rule could be plus 8, or excuse me, plus 12. So then let's try plus 12 in the next one. 7 plus 12, does that equal 21? No, 7 plus 10 is 17, plus 2 is 19. So it cannot be plus 12. Though it works for the first one, it doesn't work for all the other ones. After that, let's try multiplication. If it's going up, it's either got to be addition or multiplication. 6 times what equals 18? 6 times 3. 7 times 3 is 21, perfect. 8 times 3, 9 times 27. So we know it's in times 3 equals out, or x times 3 equals y. So we know our rule is going to be multiplied by 3. So on the bottom it says, number 1, if Ray buys 15 toys, what's the cost? 15 times 3 equals $45. Because 15 times 3, 10 times 3 is 30, plus the 5 times 3, which is 15, $45. If Ray pays $45, how many toys did he buy? So that means if our out is 45, we have to think to ourselves, what times 3 equals 45? So you have to work a little backwards. Well, how many times does 3 go into 45? Look at that. 15. Well, we just did the inverse. So how many toys did they buy? He bought 15 toys. Now, write an expression to describe the output pattern if the input of the variable is t. So instead of saying x, we say the input is t. T times 3 equals output. And number 4, what inputs and outputs should be added to the table for 20 toys? So if we had 20 toys like this, well, I'll just add to it. 20 over here, 20 times 3 equals 60. 20 and 60. Again, if our rule is times 3, we're just taking that 20 and then timing it by 3. Sally says the expression 2x describes the input-output table. So 2 times this equals this. Explain why she's correct or not right. So 2 times 2 equals 4. That is true. Sally's right. But the next one, 3 times 2 doesn't equal 5. So our input can't be times 2. 4 times 2 does not equal 6. Our input-output cannot be multiplication because they don't always go up by 2 or times 2. So then it has to be addition. 2 plus 2 equals 4. 3 plus 2 equals 5. 4 plus 2 equals 6. And 5 plus 2 equals 7. So Sally is wrong. Because the rule is plus 2. Is add to as multiply doesn't work. There we go. So you're going to be doing the next page as well, same thing. Inputs, outputs, all that good stuff. And then I'll put the answers up and you can double check and see how she rolls. If you have any questions, let me know.